Okay, so the theorem we're going to prove in this video is exactly what I hinted at in the last video, namely congruence, modulo, and ideal is saying that the cosets are equal. It's equivalent to saying that that exact thing. So let's prove it. So suppose that A I'm not going to write A plus I as B plus I because that will mean something different now. A is congruent to B modulo I. So we're going to do the forward direction. And what does it mean to be congruent modulo I? It means that the difference is in I, but this is just an element. So there exists some I in I such that B minus A is equal to I, or equivalently, B is equal to A plus I. All right, we want to show the cosets A plus I and B plus I are the same thing. So B plus I is the collection of all B plus J's. I already have a little I, so I'm going to use a J, where J is an I. But we know that B is related to A via the equation A plus I. So I can plug in an A plus I here. I'm going to put some parentheses around it. But that's A plus I plus J, where J is an I. Now I is an ideal, J is an I, and I is an I. So this guy is an I. Great. So B plus I is a collection of all A plus I plus J's, which is maybe not all of the elements of I. Maybe you can't get all of them as a sum. In fact, you can, but maybe you can't. In particular, though, this is certainly contained in A plus I. Right? Elements here are A of the form A plus an element of I. Similarly, since A is B plus negative I, by moving the I over, we get that A plus I is contained in B plus I. Okay, so we have our double containment argument. So the cosets, in fact, are the same. Great. So that's our forward direction. Let's do the reverse direction now. Suppose the cosets are the same. That is, on the left-hand side, A plus little i's, I in I, is the same as B plus little j's, J in I. Great. Let's observe something that, firstly, that I is an ideal, so I has 0 in it. Okay, so in particular, A plus 0 is in A plus I, which happens to be B plus I. But A plus 0 is just A. So A is in B plus I. This means there exists some J in I such that A is B plus J. Oh, I did this in the wrong order. That's fine. This is equivalent to saying B minus A is negative J, but J is an ideal, so negative J is there. Or sorry, I is an ideal, so negative J is there. And therefore that difference is an I. Thus A is congruent to B modulo I. And that's the reverse direction. Now, this says that congruence is the same as these two cosets being the same. And let me also notice as a corollary, an immediate corollary, let's use here, congruence modulo I is an equivalence relation. Just like we had to show congruence modulo Z was an equivalence relation, congruence modulo I is also an equivalence relation. So what this tells us then, well, sorry, how does the proof go? Sorry, I distracted myself there for a second. Well, congruence modulo I is defined using equality of sets. And so how do you check it's an equivalence relation? Well, you need to check that equality of sets, the corresponding sets that you get, are behave with, satisfy reflexive, symmetric, transitive, and so on. But it's equality of sets. Equality of sets will satisfy that. So I'm going to end it there and I'll let you think about filling in what little details there are. But congruence modulo I is an equivalence relation, just like congruence modulo an integer was an equivalence relation.